You probably don't think much about the physics of it. You just, tuck your phone into your pocket, maybe unplug your laptop, or you might be listening to this whole conversation on a pair of wireless earbuds smaller than your thumbnail. Everything is just so fast, cool, and effortless.
And that word effortless is exactly what we need to zoom in on today. It is so easy to take this level of engineering for granted. But if you stop for just a moment and consider the impossible speed of that miniaturization.
Yeah, think back just 70 or 80 years. How did a computer that literally filled an entire air-conditioned room and consumed just astronomical amounts of power suddenly become something that fits in your palm and it barely even gets warm?
And not just smaller, but so much more powerful, right?
Right.
If you talk to people, they might point to, say, better batteries or smarter software, but those are just the beneficiaries of the foundational leap.
Exactly. The massive physical turning point that really opened the digital age, it rests on one specific, ridiculously small component.
It's the single most manufactured device in human history, which is an insane thought. Yet most people couldn't even draw you a picture of it.
We are talking about the true heart of all modern electronics. It's the foundation of every digital system you use, right down to the little chip in your credit card.
Today, we're doing a deep dive into the transistor. And our mission is to explain the shockingly simple principle behind it and to tell the story of its pretty dramatic engineering birth. We're going to show you exactly how a tiny, delicate input signal learned to command massive amounts of electrical current.
And why that one small detail changed absolutely everything. Okay, so let's unpack this tiny controller. To start, the word transistor itself. It holds a bit of a clue, or maybe a bit of a misdirection.
Right, the term was coined way back in 1947 when it was invented. And the word is, it's what I call a portmanteau. It's linked to transfer and resistance.
Transfer plus resistor.
Transfer plus resistor, exactly. Right. And the implication is that the device is somehow moving or, manipulating resistance inside a circuit.
And this is where we have to stop and immediately clear up a really common misconception, one that's kind of baked right into the name.
Yes. A transistor does not, strictly speaking, transfer resistance. That's not a physical thing you can move around. It controls the electrical path.
So the name is more of a clue to its function than a literal description of the physics?
Perfectly put. It's an etymological clue. If we define it simply, a transistor is a semiconductor device that allows the flow of current running through it to be controlled by changing a small input voltage or current applied to one of its electrodes.
The control gate or the base?
Often called the base, yes.
But wait, if the name is a bit misleading, if it doesn't literally transfer resistance, how did that slightly inaccurate name stick and become, one of the most famous words in all of technology?
Because it captured the effects so simply, it acts as if the resistance is changing. But what this all means for the big picture is it's much more powerful than just terminology. We can boil the entire function down to one powerful statement. A small change at the input, that tiny signal, can cause a significantly larger change in the output current and voltage. This control, this ability to magnify a whisper into a shout, that's the principle that changed everything.
To really get your head around that power difference, we need to picture it. So let's try to explain this with your eyes, using an analogy everyone has in their house. A faucet, a water tap.
Okay, yeah, that's a perfect one. So imagine the main pipe that's feeding that tap. That pipe is carrying a large, constant flow of water. That's our main current. It's the big electrical power source we want to control.
And the handle, the little knob you turn with just 2 fingers, that's our small control signal.
Exactly. You, the user, you apply a tiny, almost negligible amount of force to that small handle. And crucially, that handle isn't physically moving all that water in the pipes. It's not pulling it from the source.
Right, it's just acting as a valve, a little choke point that dictates how much water can flow through.
It's an intermediary. Small control input, massive consequence for the output flow.
Okay, the analogy is perfect. But now we have to connect that small physical twist of a faucet handle back to the confusing world of physics inside a solid piece of silicon.
And that's the magic of the semiconductor. We can keep this totally formula-free, but here's the key mechanism. Inside that transistor, that tiny input signal, a little bit of voltage, it changes the material's internal conductivity.
Conductivity, which is just a measure of how easily electrons can move through something, it's the opposite of resistance.
Precisely. We're talking about materials like silicon or germanium. At their heart, they aren't good conductors, but they aren't good insulators either. They're semiconductors. And they can be subtly engineered through a process called doping to have layers that are a little bit electron-rich or a little bit electron pour.
And those layers create a kind of barrier, almost like a locked gate.
Yes. And the small input voltage is the key to that gate. It physically pushes or pulls the charge carriers, the electrons, within that control region. And by doing that, the control signal effectively makes the path for the main current suddenly wider or narrower.
So the input signal isn't carrying the power. It's just telling the gate to open or close, which allows that massive main current to flow through. That's why the small change leads to a huge result. It's an amplification of authority, not an amplification of power.
That is the perfect way to phrase it. You're controlling the tap, not pushing the water. And this unique, reliable control gives the transistor two essential superpowers that are the bedrock of all modern technology.
Okay, superpower number one, the switch.
This is its digital role. This is the foundation of all computing. Because that control signal dictates the path's width, you can use the transistor in two simple extreme states. You can tell the gate to be fully off, where current is almost completely stopped, or fully on, where it flows freely.
And that's the logic of 0 and 1, the simplest possible decision. Every calculation, every piece of data, every instruction from a supercomputer down to a tiny calculator, it's all just billions of these tiny switches flipping on and off at incredible speeds.
And if that was all it did, just simple on-off switching, it would still be the most revolutionary invention of the 20th century. But then we have superpower number two, the amplifier.
So what happens if we use that control signal more gently, instead of just slamming it fully open or fully closed?
This is the beauty of the smooth control. The transistor doesn't just have to be on or off. It can open gradually, proportionally. If you apply a very small change to the input, you get a corresponding, but still proportionally larger, change in the output current.
So we're not dealing with discrete digital steps anymore. We're in the world of continuous analog control.
Precisely. And this is critical for taking weak, real-world signals and boosting them. Think about a sensitive microphone picking up your voice, or an antenna picking up faint radio waves. That electrical signal is minuscule. If we only had switches, your music would sound like Morse code. Just clicks.
Right, on and off. But because the transistor can act as an amplifier, it takes that small, weak input wave and uses it to perfectly shape a much larger, stronger current.
And the output is a significantly amplified signal, whether that's smooth, high-fidelity sound driving a speaker or a clean radio signal for your phone. The switch builds the computers. The amplifier makes the real world intelligible to those computers.
It's just incredible that the same tiny component does both of those things flawlessly. But before this tiny, cool, efficient device existed, the world of electronics, it looked dramatically different. We have to rewind to the era before the transistor.
We have to rewind to the age of the vacuum tube, and I mean that literally.
You're basically talking about building the future on heaters. Vacuum tubes were the active components back then, the original switch and amplifier. But they were these bulky glass envelopes, they were fragile, they needed high voltages, they guzzled power.
And they produced immense heat because they relied on a glowing hot filament, just like an old incandescent light bulb.
And that heat was the ultimate killer, wasn't it? It limited how many components you could cram into one space, and the filaments would just burn out.
All the time.
Yeah.
Like a light bulb, they had a short shelf life. Engineers were constantly swapping them out.
Which meant that complex electronics like early computers or the telephone switching systems, they were massive, unreliable, cost a fortune to run, and needed endless maintenance.
And this frustration brings us right to 1947. And to the high-stakes drama that was unfolding at Bell Telephone Laboratories in New Jersey. The pressure was immense. The phone system was constantly failing because of tube burnout. They needed something smaller, cooler, and just infinitely more reliable.
This is where our three key figures enter the story. John Bardeen, Walter Brattain, and William Shockley, the leader of the solid-state physics team. Their goal was simple in theory: create a solid-state device that could control current without a vacuum and without a hot filament.
And after years of intense, sometimes very competitive research, they had their first breakthrough in December of 1947. They demonstrated a working prototype, the point contact transistor. It was this delicate, hair-thin piece of germanium with two little gold contacts just touching the surface. But it worked. It proved current control was possible without a glass tube.
That must have been a monumental moment. I mean, they proved the concept.
It was. But here is the critical distinction. The one that separates a successful lab prototype from a revolutionary piece of technology. And that is repeatability and manufacturing stability.
Ah, the crucial engineering obstacle. The thing that separates a Nobel Prize curiosity from a consumer product you can actually sell.
Exactly. The early point contact devices were notoriously temperamental. They relied on two tiny points physically touching the semiconductor.
Yeah.
Purity, vibration, even a slight temperature change would make them drift. They worked, but they worked inconsistently.
So one transistor might open its faucet at, say, 2 volts, but the very next one, built the same way, might open at 3 volts.
Precisely. And if you're trying to build a complex system that needs millions of components working in perfect harmony, you just can't rely on that. If every tiny faucet opens differently, the whole system fails. Mass electronics demands billions of identical, predictable components.
So the real engineering genius wasn't just inventing the transistor, but designing a version of it that could actually be industrialized.
That's where the second wave of development, spearheaded mostly by Shockley, came in. They transitioned to a much more robust, junction-based transistor architecture. So instead of relying on these finicky physical contacts, they used internal, built-in layers of doped silicon, the PN junctions, to create that controlled gate.
By building the faucet mechanism right into the crystal structure itself, they solved the repeatability problem. They went from a delicate, touchy device to a predictable, industrialized valve.
And once that hurdle was cleared, the transistor won.
Yeah.
Immediately. The shift was so rapid, and the comparison to vacuum tubes is just staggering on every single metric.
Its size, first and foremost, it became microscopic almost overnight.
Heat production plummeted, which eliminated the constant need for cooling. They required far less energy, making battery-powered devices suddenly feasible for the first time. And reliability shot through the roof. No fragile glass, no hot filaments burning out.
And crucially for the consumer age, once manufacturing scaled up, they were vastly cheaper. That economic factor is what democratized electronics.
Absolutely. The 1960s saw that rapid shift. Electronics began to shrink, moving out of these highly specialized labs and into the home. It's why hearing aids got tiny, why pocket radios became a cultural phenomenon, why calculators moved from a desk to a briefcase.
So the small signal didn't just win, it dominated. And it introduced the key concept that defines our modern age, scalability. It became a building block.
The transistor is a brick you can repeat forever. Unlike the vacuum tube, which was limited by its size and heat, the transistor could be shrunk down to microscopic dimensions, and it still worked perfectly.
One transistor controls current. 1,000 create symbol logic. 1,000,000 create complex processors. That ability to just infinitely repeat the same small, predictable function is what opened the door to integrated circuits.
This is the trajectory that led directly to the modern microchip. The core principle, that tiny control signal modulating a larger current, it stayed the same, but the sheer density just exploded. Today, you're putting billions of these faucets onto a single piece of silicon the size of your fingernail. And that is why you have a supercomputer in your pocket.
It truly is mind-blowing, all of this complexity, all the speed and memory resting on such a simple principle of control.
It is. The final takeaway for our deep dive today is just that simple but profound core idea. A small signal controls a large current. That dual role as a precise switch and a smooth amplifier is the foundation of the digital world we all live in. Without it, none of this works. We'd still be in a world of hot, unreliable glass tubes.
And this leads us right to our final thought for you to consider. The shift from one temperamental transistor to a part you could manufacture was a huge engineering masterpiece.
It was. But the leap from one discrete transistor, that little piece of plastic with 3 legs, to billions connected on a single chip, that's another story entirely. It required a completely new breakthrough.
So if the transistor is the fundamental faucet of electronics, who taught humanity how to package millions and now billions of these faucets together, connect them flawlessly, and force them to work as one massive, integrated, and impossibly complex system.
That is the story of the integrated circuit, the microchip, the invention that took the transistor and made the modern world possible. And that, well, that we'll save for the next deep dive.